Alright, hello everybody, my name is David Bronicki, and today I'm going to be talking about the influence asteroids can have on the LISA orbits. This work was done in collaboration with Bolen at Grand Valley State University and Larson at Northwestern University. I'm going to start out with a bit of motivation for why we should be looking at these asteroids to begin with, a mass estimation technique that we came up with to help with this, and of course the influences that these asteroids do have. So if we consider an asteroid in the asteroid belt, that's going to produce a tidal force on the LISA constellation, and this tidal force could potentially influence data collection and analysis for LISA. And also, over a long duration, it can actually distort the shape of the constellation, which would also impact data collection. So, of course, doing any simulation for this requires information on a lot of asteroids. So for this, we pulled data from the JPL Small Body Database, which has information on over 700,000 asteroids. We specifically pulled the orbital parameters, standard error thereof, and the absolute magnitude of these asteroids. If available, we also pulled the mass information. However, that is a very, very sparse amount of information. We don't have the mass information on many asteroids. And for that reason, we had to come up with this mass estimation technique. So this technique assumes spherical symmetry for each of the asteroids, and then we use the albedo, which is essentially how reflective the asteroid is, and the absolute magnitude, which is how much got reflected, to get an estimate for the radius of the asteroid, and therefore the volume. And when you combine this with the density, which you can get by taking sort of average density for the asteroid type, then you can get the actual mass of the asteroid. And when we compare these results to the masses of known asteroids, which there's only actually about 20 asteroids where we actually know their mass, then this technique typically gets us around within 50% of the known mass. So now that we have these masses, we can throw this into a simulation. So the first simulation is to see what sort of acceleration noise these asteroids will produce. And so we don't actually evolve the perturbations, we only keep track of how much acceleration there is, and then through Fourier analysis we get what sort of acceleration noise it would produce. So the final simulation used only 10,000 of the heaviest as opposed to the 700,000. Surprise, 700,000 is a bit computationally heavy, but as a point of reference, the largest asteroid in the belt series accounts for, I believe, around a third of the mass of the entire belt. So these 10,000 heaviest will account for the vast majority of the mass here. Also, as a side note, through the course of this project, I ended up coding this simulation 3 times in 3 separate languages. The first time I did it in Python, and I made a benchmark for how fast it was going, and it took 83 seconds. When I moved over to C++, the same benchmark took 4.5 seconds. So that's a testament to how powerful a compiled language can be in comparison to an interpreted one. And I eventually moved over to CUDA, which is a GPU programming language, which allows you to code all of this in massive parallel. And that brought it down to 50 milliseconds. So if your project lends itself to parallel, it's a pretty powerful tool. Yeah, so this simulation produces this graph here. So on the right here, the blue line is the LISA noise curve, and the red line is the acceleration noise produced by the asteroids. And you can see that they are several orders of magnitude different there, indicating that the asteroids have negligible impact on LISA, so there will be negligible signal loss. So for the next simulation, we want to look at the long-term behavior of the constellation. So for this, we are doing perturbation, so we are evolving the changes to the LISA orbits. And so we used 2 separate simulation techniques. One of them was Runge-Kutta dynamic time step, and this was done in Euclidean coordinates. and the other one used orbital element coordinates, but only used an Euler method algorithm. So it's less accurate, however, they give the same result, indicating that the two simulations are working correctly, which was the main motivation for doing two separate simulations here. So when we look at the results from those simulations, the main headline one is on left here. This is the actual perturbations of the arm lengths of LISA. So arm 1 would be the arm that is opposite to satellite 1. It would be this arm here if this is satellite 1, and the same for arm 2 and 3. And this is on the order of single meters as opposed to the 2.5 times 10 to the 9th meters of the actual arm length. And of course you might be looking at this graph on left and be thinking, wow, that's just a lot of graphs on top of each other. How do I look at this? We were thinking the same thing, so we boiled it down to this graph on the right here. This is the perturbation not of the arm lengths, but instead of the enclosed area of LISA. And so the idea there is that you're looking at this area here, and as it gets distorted, it might get smaller, might get bigger. We keep track of that change. And a nice little result is that for an equilateral triangle, which of course LISA is roughly equilateral, then if you keep track of that perturbation of the area, it comes out to be a multiple of the sum of the perturbations of the arm lengths. So that means that these two graphs are intimately connected. If you sum up everything on the left, then you get the same shape as what you see on the right. Also, on the right we have the mission start time, which was essentially arbitrarily chosen to be at 2029. And 4 years later we have marked in red the short duration mission end. So this indicates that if this is sizable enough to be necessary to take into account for data analysis, then you will need to take it into account even for the short duration mission. And so that's the extent of what we've done for this project. We use this new mass estimation technique that uses the albedo, absolute magnitude, and asteroid type. We simulated 10,000 asteroids to see what sort of acceleration noise they produce, and we found that it is negligible for LISA. And we simulated it only with series at the time of this recording to get the constellation geometry perturbation, which we found to be the fractional perturbation to be on the order of 10 to the negative 9, which results in a length perturbation, absolute perturbation of on the order of meters. So work left to do. Like I said, we only have series on that constellation shape simulation. So we would like to throw in more asteroids just to make sure we have a complete picture of that. And we would also like to extend some of what we've done here, so we'd like to look at near-Earth objects. Those will of course make more transient signals because the asteroids will pass by closer to the LISA constellation itself. And we would also like to extend that mass estimation technique if possible. Like I said, it is a new technique, so other projects might find it useful. And yeah, that is all that I have. Thank you.